Hi, my name is Mark Valladares. I'm a tennis coach in Kansas City who studies body and brain dynamics in an effort to both understand body and brain dynamics and in an effort to inform the discipline that I'm in. So my talk is entitled Proprioceptive Feel as a Summation of Oscillatory Resonance. Basically, having connected the flow state of high-performance athletes and musicians, and there's evidence from these studies by Charles Lim on this, with whole brain criticality, we have this idea that the body's perceptive faculty can be primed for a heightened sensitivity to a particular response, and this constitutes a sort of predictive cue for proprioceptive feel. The summation of oscillatory resonance, which is neural, it's the synchrony of these neural oscillations, at the point of the body's response to stimulus would constitute the vibrational signature of that feel state. It doesn't determine the feel state, it doesn't resolve the hard problem in consciousness, but it gives us a quantifiable basis from which we can maybe describe the constraint of synergies as a result of that predictive anticipatory cue. So the proprioceptive feel is basically induced from global oscillatory resonance patterns, which in turn are transduced from mechanosensory distortions in what I'm calling, and what has been referred to by Turvey and Ingber as the multifractal nested tensegrity grid of the body. The consolidation of vibrational signatures constitutes a harmonization of potential sets of subjective states. So basically, the summation process is assigning a qualitative state to this sensory input that's coming in, and it can be defined as a particular feeling once your perception kicks in, but it can actually happen below your perceptive awareness, and that's what the beauty of studying proprioceptive feel gives us. Coupled in this talk is this idea that the microtubulin polymers, which form the basis of the tensegrity grid because it's a nested tensegrity structure, they provide, because they're both scalar, they have a base of 13, and tensor, they have this flex and this relax to them. They provide an information processing topology, and so we'll get a little bit into that. The crux of it is that proprioceptive feel, the feel state is something that is occurring at the fine scale, and when you're feeling something, that's kind of where your consciousness is, and there's this toggle between sort of perceptual awareness of the feel state and sort of the intrinsic feel, and proprioception is a good way to sort of study that, because we get posture, we get the subattentional sort of response in the form of haptic feedback to stimulus that can occur before you're actually aware that you've responded. And this is an evidence, and it's easy to study, so it becomes a great domain in which to do science on something like the feel state. What all this puts into perspective is the idea that consciousness is real, we're using it, and the elephant in the room is sort of that consciousness is the statement that I make here, that consciousness attunes criticality. And criticality, you might wonder, why is that consciousness necessary to define? Why attribute agency to criticality? Couldn't criticality just be self-organizing, which is in evidence? And but because consciousness is in the system, because you can't push it off the table, and because biological systems are imbued with criticality across scale, you could also argue that criticality is essentially, attuning criticality is essentially what consciousness is doing. And you see this from the recruitment of proteins in biological systems that are imbued with criticality at a disproportionate ratio. I think that it's 10 to the minus 50, so it's really highly unlikely that we get this array of proteins, many of which are infused with criticality. So consciousness likes criticality, and criticality, the system attuning itself to these critical points where you can get a cascade of effects becomes really important understanding the process that's at work here. So I'm pointing to one of the fields I'm pointing to is out of the cognitive sciences, a survey of performance studies. There's an anomaly that occurs that the late great Guy Van Orden points to as an indication of this concept of fractal time, and basically what you see is as you look at the body of data, you have these sort of power law distributions, the 1/f fractal noise that appears in the data, which indicates that you're working with a nonlinear dynamical system, and you have to account for the fact that motor control, there's a perceptive anomaly involved with motor control, memory tasks, and it might be linked to the instructional that is given in these sort of cognitive domains when people are conducting these experiments. That's certainly a factor, but what we see is sort of a dissipation of control, and if you don't see that, then you're basically not doing enough studies. So critical states are something that we're gravitating to, and basically what's happening here is that you have this behavior that is established, and as soon as you do, you have this this domain in which mind and behavior are seeking critical points, so that you do have an interplay of the control of these changes. So small inputs, small stimulus can trigger qualitatively different modes of behavior, and this leads to the concept of these constrained synergies, the body constraining the synergies of the mind, behavior constraining mind, so the mind is not necessarily a governing. So he conceptualizes it as a blue-collar relationship of mind to body, and you know, in which, like I said, consciousness is seeking these critical points that enables these nonlinear dynamics to sort of unfold, and that brings us to bifurcation theory. Typically, the modality of motor control is a top-down, it's understood as a top-down process. The neurons are you know, governing the behavior and the dynamics of muscles. In terms of the neuroscience, like I said, this is fairly well understood, but it doesn't account for, there's some paradoxes here in terms of how to, you know, where is the control actually happening, and the signaling process is so slow with neural conduction that and these response times are so fast that we basically have to account for a process that is sort of more together than it appears at the time that the inputs are occurring. The fractal physiology, the whole body is a fractal system. You have this inversely proportional relationship to the structure and the size and the number of constituents of a particular system, and that in itself imposes a kind of constraint on the system. And so fractal physiology, criticality, which we just kind of covered, the system seeking these critical points, and then tensegrity, which we're going to get into here in a sec, will really begin to sort of explain how this whole dynamic comes together. And then the statement control is about understanding constraints on different time scales, and this is really kind of the essential piece of the information processing that has been fleshed out by Anirban, and the potential for that to occur at the tubulin level, at the fine scale, indicates that we're kind of on the right track. So Guy Van Orden and Chris Kello basically institute this idea that behavioral variation is a fractal, cognition is long-range correlated across time scales, there's a dissipation event basically that occurs with it. Coordination of brain and body has its basis in metastability, so the system doesn't just achieve a level of control and maintains it, it's always dissipating, and this is kind of what you see, and there's this sort of dynamic instability, the stability provided by behaviors, the instability imposed by the injection of mind. Tensegrity is originally derived from Bucky Fuller. It's like a geodesic dome that you can compress and it pops back out. It has this conformational stability. It's structural integrity from a system of compression and tension, and that's similar to what's happening in the body with the muscles and the bones and the fascia wrapped around it. It's not just sitting there hanging on. The bones aren't just sitting in there, in vague space. So there's this constant tension in the system, a pre-stress, if you will. And Donald Ingber at Harvard, really kind of attacks this concept, demonstrating how mechanical forces influence cell destiny, and you get this mechanotransduction at the cellular scale that is virtually instantaneous, basically an acoustic wave, that can determine how genes express themselves based on the tension in the extracellular matrix. And so that gives us a multifractal nested tensegrity structure. So in other words, just as the bones and the muscles and the fascia are all providing this tensegrity structure, if you unpack that, you go to this finer scale in which you have the tubulin as the bones, in some sense, actin myosin providing compression, the membrane, and so you get this conceptualization of the brain and the body as an excitable media with these sort of interwoven synergies, and so the tensegrity yields this picture of a collection of these synergistic domains, and as you go from hand to limb to body to trunk, and the constraints are coming from the thicker processes, that principle is still in place. And it gives us a conformational metastability. And so the whole system is essentially in touch with itself from the cellular level to the macroorganism. Any distortions in tension anywhere are detected everywhere. And so it has a sense of itself. So proprioceptive feel can be defined within that perceptual system as the body being kind of aware of itself and the adjacent environment in response to it. And Turvey develops this idea beautifully. So what we're getting to tie together here is the idea that the microtubulin polymers are propagating mechanical forces, so they have an inherent sense of the pre-stress tension, but as they're also capable of being conduits of oscillations, and this is what they're doing. And these oscillations end up being, in neural systems, end up being associated with processing and awareness. The fact that the tubulin are scalar and tensor are really important. The scalar, they have a base of 13, so basically what they're doing is it's an information processing topology. There are these harmonic permutations that are generated from noise as it comes in, and information gets integrated. This is the work of Anirban Bandyopadhyay, and here you can see him sticking a direct measurement into a probe into a microtubulin bundle and basically reading the activity. And one of the things that happens out of these, when he starts to probe these tubulins, is that because of the resonance patterns, the small amount of energy that is coursing through there, through these resonant frequencies, can yield a greater amount of energy. And so that's kind of an unusual an anomaly that tripped him a little bit, but it was verified elsewhere by this guy named Muller, and so this is really the current of thoughts and meaningfulness having this sort of effect that can scale up. And here we see the breakdown of it into these three bands, and he calls this the triplet of triplet configurations. And here what he's done is he's gone inside a neuron, inside the microtubulin, and he sees these three bands at three different frequencies. And so he calls it the triplet of triplet configuration, and then each of these bands has these 8 sort of peaks, and so the 9 into 8 produces what he calls 72 clocks. And we were talking about how control is about imposing constraints on a fractal time scale, and here we see the evidence surfacing for exactly that. So it's as if as these patterns are coursing through the body, it's understanding the role of the mind and behavior in the context of fractal time. This is a centriole, which also, I throw this in here to sort of reflect how every cell in the body has this, and this is where the tubulins converge and are made, basically, and it's also a triplet. It's a triplet configuration, and so it's theoretical, but it's possible that every cell would have access to those resonance patterns. Intrinsic feel and qualia have to do with this is a study from Ross that I'm pointing to indicate how the beta band, which is very in strong evidence in association with motor behaviors from Parkinsonian studies, but proprioception in this study or haptic feedback is correlated with beta synchrony because of the time frame. The onset to steady state is just 10 milliseconds, which is the amount of time that you can respond to stimulus as it comes in. And you see this in tennis where people are, will respond to a ball below their awareness of it. It happens quicker than you can sort of perceive. You're responding to it, and then there's a perceptual awareness that's tagged with gamma synchrony at a half second or 400 milliseconds. The intrinsic feel is essentially the pre-stress state of the bio-tensegrity grid. So the grid has this pre-stress that defines it. So deviations in tension will alter the field. If those deviations in tension, if those distortions in tension are significant, then you get a qualitative change in the state. So all of the input coming in are, in some sense, potential subjective states. And then as it achieves synchrony, you have this, you basically have this perceptive anomaly, a singularity event in which you're perceiving it a certain way. I want to end with this brief discussion of the Tripinski gasket and how it influences, and this will help us understand how energy dynamics at a fractal scale are sort of at work. Now, the Tripinski gasket, we don't know if it's in the body or not, but this is just to illustrate fractal scaling, and basically this is a triangle in which you systematically remove these equilateral triangles from it, and then you get an infinite amount of perimeter as the area diminishes. And so this is a nice way to conceptualize kind of the anomaly of what we see when teaching tennis. So if somebody's learning a skill, basically, there's a tremendous amount of energy that goes into creating this picture of the stroke. You probably break it down into three parts: the setup, the hit, the follow through. And then as the person practices that, they begin to anchor to one piece of the swing that will pull all these chunks together. And then as they continue to do those iterations, the energy then becomes more of a feel state. So then as it goes to the feel state, what we expect is to see less use of area. So it will disappear out of the bigger triangles, and the information about the swing will be dispersed as a feeling. And that's eventually what the forehand becomes and the serve becomes. So that's kind of how I'm tying this to tennis. Thank you very much. That's the presentation.